Okay, let's talk about deformation. As deformation occurs, intermolecular forces arise that oppose the applied force. If the applied force is not too high, these forces resist the applied force and allow the material to resume its original state once the load is removed. A larger applied force may cause a permanent deformation of the material or even structural failure. There's different types of deformation that may result from variations in the type of material, size, and of course the forces that are applied. Types of deformations include the following. Elastic deformation. This can be reversible. Elastomers and types of memory metals, like nitinol, exhibit huge elastic deformation ranges, as does rubber. Plastic deformation. This may be irreversible also. Soft thermoplastics have a rather large plastic deformation variance, as do ductile metals such as copper, silver, and gold. Metal fatigue. This occurs primarily in ductile metals. Metal fatigue has been a common cause for failure, especially before the process was well understood. Compressive failure. This is applied to bars and columns, etc., which leads to shortening. Loading a structural object or specimen can increase the compressive stress until it reaches its compressive strength. Fracture. This may be irreversible. All materials eventually fracture if enough force is applied. What figure 8.3 out of your textbook, and what do you observe in these materials? Now we have 5 samples of the same length, diameter, and general configuration before they tested it. Then they tested it on a tensile testing machine where it pulls the material apart until it fails. And you can see that there's a lot of plastic deformation, of course, in the plastic parts themselves. We have some necking here. And this cast iron part here, you can see has a clean break. That's brittle fracture. The aluminum had some necking. It pulled apart before it did finally fracture. And steel also experienced the necking in the material. This is going to be a soft 1018, a mild steel. Ductility and brittleness. Again, ductile materials stretch or neck before they break. Brittle materials have little or no ductility and stretch very little before failure, if at all. Don't confuse with elasticity, which returns to its original shape. The stretch is permanent or deformation. Ductility and brittleness. Cleavage occurs in brittle materials, and ductile failure is known as shear. Remember those two terms and what they relate to. Cleavage to brittle, shear to ductile. Cleavage equals brittle failure. Brittle fracture in metals at the microscopic level, also known as ideal cleavage or pure cleavage. It occurs only under certain well-defined conditions, primarily when the component is in its single crystal form and has a limited number of slip systems. This is described as cleavage fracture. Cleavage fracture of metals occurs by direct separation along the crystallographic planes due to a simple breaking of atomic bonds. Its main characteristics are that it is associated with a particular crystallographic plane. It is increased by lower temperatures and higher strain rates. More commonly in metals, the fracture surface contains varying fractions of transgranular cleavage and evidence of plastic deformation by slip. Cleavage fracture surfaces appear in steel due to sudden or impact loading, low temperature, high levels of constraint, ambient temperature, or heavily cold work parts. The cleavage fracture of steel is generally explained by the weakest link mechanism, which is differentiated from yielding and work hardening. Under normal circumstances, face-centered cubic FCC crystal structures do not exhibit cleavage fractures, as extensive plastic deformation always occurs in these materials before the cleavage stress is reached. Figures 8-5, 8-6 give really good examples of cleavage failure. And you can see the grains, the granular surface of where the break happened. Shear, which equals ductile fracture. Ductile failure is one of the most crucial concepts in material engineering. In general, a ductile failure is defined as a body going through separation due to imposed stresses. Almost all engineering materials undergo only two types of failure fracture modes, ductile and brittle fracture. Ductile materials exhibit massive amounts of plastic buckling or deformation in comparison to brittle materials. In ductile failure, the crack grows at a slow pace and is accompanied with a great deal of plastic deformation. In this case, the crack does not expand except when high levels of stress are present. In almost all material design situations, materials that exhibit ductile failures or fractures are preferred for various reasons, such as ductile materials deform plastically, slowing the fracturing process and allowing more time to correct the problems so they can see it as it's happening. Higher amounts of energy strain are required to deform a ductile material. Ductile materials are forgiving, and any error in the design process does not result in a catastrophic failure. By understanding ductile failure, engineers are able to develop more dependable and safer industrial products and materials. Figure 8.8, an example of necking down, and 8.7 is an example of shearing. You can see how the forces, even though it's being pulled apart, the forces are coming across it like that, and it's causing the material to shear. Shear failures have two forms: slip failure and twinning failure. Which form depends on how the atoms are displaced within the material. We're going to look at these. Slip failure. Slip failure for aluminum, because it's ductile, so the shear failure is the slip form. Instead of dividing in the middle of the crystal, the atoms slide past each other row by row. The part deforms, becoming longer and thinner. Here's figure 8.10 out of your book. It shows you slip failure on the atomic level and how they're slipped by each other as they're failing. You can see that this material has slipped 2 atomic levels, 1, 2. So the slip occurs on lines of crystals called the slip planes. Remember that? And the blocks of atoms move in layers a step at a time. That's the deformation. Multiple slip planes in action. Now here's your slip bands. Figure 8.12 in your book. A fine example of slip planes. Now let's talk a little bit about twinning. Twinning is similar to slip. Both are ductile failures resulting from shear. It's a zone within the crystal structure is deformed from its original space lattice. The two boundary lines separating the deformed zone from the non-deformed zone are known as mirror lines or the twinning planes. So you think twins, same on one side as the other. And there you have the twinning plane, 2 twinning planes, and you have the deformation on either side. So mechanical twinning occurs in metals that have bodied center cubic BCC and hexagonal closed pack HCP crystal structures at low temperatures and at high rates of loading, or otherwise known as shock loading, conditions under which the slip process is restricted. They are more likely to form deformation twins when strained because they rarely have a sufficient number of slip systems for an arbitrary shape change. The quantity of bulk plastic deformation from twinning is relatively small compared to slip. However, the real importance of twinning lies within the accompanying crystallographic reorientations. Twinning may place new slip systems in orientations that are favorable relative to the stress axis such that the slip process can take place. Twinning differs from slip in several respects. First, for slip, the crystallographic orientation above and below the slip plane is the same both before and after the deformation. For twinning, there is a reorientation across the twin plane. In addition, slip occurs in distinct atomic spacing multiples, whereas the atomic displacement for twinning is less than the interatomic separation. Slip occurs on a relatively widely spread planes, but in the twinned region of the crystal, every atomic plane is involved in the deformation. Large and small crystals, crystal grain size influences the strength and ductility of the material, as we talked about in the previous slides. Small crystals are stronger than the large ones. Slip planes move along the crystals, but their boundaries tend to block the crack travel, and smaller crystals equal more boundaries and greater fracture resistance. In figure 8.15, the grain boundaries help to prevent the slip. Grain size also affects slip. Smaller the grain size, again, the more resistance to slip. It has some borders there that can protect it from breaking. Work hardening. Work hardening is when a material is stretched, or a phenomenon called work hardening or strain hardening occurs. The material receiving repeated applications of low-level force becomes stronger, harder, more brittle. Normal work hardening is considered a natural benefit sometimes. Sometimes. Work hardening is kind of an anomaly. Why this happens is sometimes poorly understood. Normally, work hardening is considered a natural benefit. Materials while we're machining, work harden while we're machining. That is not a benefit. That is something we don't want to happen. A lot of different stainless steels, as you're machining them, the material will start work hardening, and all of a sudden, where you were cutting nicely, your tool bit that you're using starts burning up because the part is so hard. Or you go to drill it and the drill breaks off in it because it's work hardened. So you have to be very careful with your speeds and feeds and using coolants to make sure that your material isn't work hardening while you're working with it. Cold working processes such as forging, extruding, rolling, and drawing add strength to the material as a result of work hardening. And it happens on the atomic level, and it just pushes those atoms closer and closer together, which hardens that work.